I guess we can move on to the next one. This one is going to give you the Word2vec algorithm. This is more modern when it comes to learning word representations. This is an assignment for you to watch. Actually, what I want you to do after today is to watch this slide, this slide, this slide, and the other one. You can just click on this link and watch the corresponding YouTube video. And then here I'm going to answer questions and give you an overview of what we are actually doing. Let's start with this evaluation. We just saw this evaluation. You are either going to do syntactic evaluation or semantic evaluation. Here's another example. Berlin to Germany is equivalent to France to what? And then your algorithm needs to say Paris. And then you're going to count the times that it is correct. And this is semantic analogy. This is what you want out of your vector representations. And this D is exactly the cosine similarity distance. Here, we are working with a different loss function. Previously, our objective was, given the previous words, predict the next one. This is another objective function. You're saying, given the middle word, predict the words in the context. Given, for instance, the word of here, predict representation. So you're going backward. You're also able to skip 2 steps, predict the previous 2 words, predict the next 2 words. That's your job. The model is no longer nonlinear. It's a linear model. And why is it linear? Because you go from high dimension to low dimension, and then from low dimension to high dimension using vector matrix multiplication. For each word, you're going to have a vector representation. And then the way that you're going to model the probability of words being in the context, for instance, you take a pair of input and output word. This is input, output word. The way that you're going to do it is you have a vector representation for your input word. You have a vector representation for your output word. These are the entries of these projection matrices, capital U, capital V. You multiply them together. You turn them into probabilities. Now that's going to give you a probability to work with. You can augment your data set by adding phrases, for instance, New York Times. And the way that you do it, you count the number of times that New York are appearing together in your corpus versus the individual number of times that they are appearing, maybe in different contexts. And this has to be bigger than a threshold. If that happens, then you're going to include New York in your vocabulary. So you're increasing the size of your vocabulary. And then you do that another time. Now that New York is part of your vocabulary, you can look at New York Times and consider that. There is a catch here. Everything is beautiful, except for one thing. This summation here is expensive because you're doing a summation over your entire vocabulary, which could be millions of terms. For those of you who took part 1, you know that for ImageNet, we had 1,000 classes. Here you have order of millions or tens of millions words. And this is going to end up being the bottleneck. One way to deal with that is to use hierarchical softmax. And the idea is turn this into probabilities of going left or right. If you go left, you don't need to consider the vocabulary on the right, the rest of your vocabulary on the right. If you go right here, you're removing this part of your vocabulary. You don't need to consider that. And this way, you can write down your probability. There is actually a smarter way of doing it, and that's called negative sampling. You can take a log of this probability here. It's going to get rid of this exponential term. There is going to be a log of this summation, or minus the log of this summation. And then you can approximate that using Jensen's inequality. You can take log and bring it inside. And then you can do sort of mini batching over your W size. Rather than considering all of your vocabulary, you can consider a few of them that you randomly select. This was some hand wavy. It was just another interpretation of why negative sampling works. Actually, there is more details in the YouTube video. I spent 2 sessions on that. And this is much less costly. K is a hyperparameter that you choose. It could be much smaller than this W here. For instance, this could be in the order of 5 or 6 examples. So what are you doing? You pick word of, you look at the word to the left. If it's the correct word, increase its probability. That's nice. At the same time, show it a couple of words that are not likely to show in the context of off. Maybe off is a bad example, maybe representation. You increase the probability of distributed happening. At the same time, you are decreasing the probability of a couple of random samples from your dictionary. For instance, compositionality, you're going to decrease its probability. And that's how your objective function is going to work. And in the end, you are optimizing over your word representation or your embedding matrix. I think it's a good time for me to stop. For those of you who have questions, I'll be around. For those of you who want to leave, you can leave. Next session, I'm going to cover this again. So don't worry about it. So watch the videos and then come back.
Thank you.